So, in this video we are going to discuss another important data structure, that is heap. So, let me erase this thing. So, it is a clever partially ordered data structure. So, you can consider, so heap is not randomly ordered. So, it is a partially ordered clever data structure and it is specially used for priority queues. So, it is generally used for the implementation of priority queues, and priority queues has a lot of implementations. So, where priority queue is used, so priority queue is used in job scheduling by the operating system. So, job scheduling by operating system. So, here priority queue is used. So, in the traffic management by communication networks. So, in short I have written CN. Then in several other algorithms like Prim's algorithm, Dijkstra's algorithm, then Huffman coding, encoding, and some other applications are there. So, these are the major important applications of priority queue. So, heap is a partially ordered data structure and generally it is implemented or generally it is used for implementing priority queues, and priority queue has a lot of applications like job scheduling, traffic management, Prim's algorithm, Dijkstra algorithm, Huffman encoding, and many other applications of priority queues are there. And also we can use this heap in one important algorithm, sorting algorithm, and that sorting algorithm is heap sort. So, here also we can use heap. Then what is the definition of heap? So, we can see a heap can be viewed as a complete binary tree. So, it is like a complete binary tree. So, what is a complete binary tree? So, complete binary tree where all the labels are full except possibly the last label, and the last label is filled from left to right. Suppose consider this one, suppose this is one node. So, it is label 0 you can consider, or label 1 you can consider. So, assume this is label 0. So, it is label 0. So, this is the root node in a binary tree. Then like this is label 1 you can consider the next label. Then this one, this one, this one, this one, so this one. So, here consider this binary tree. So, this binary tree is a complete binary tree we can say, because all the labels are filled except the last label. So, this is label 0. If we say this is label 0, or in short I am writing L0, this is label 1 and this is label 2. So, I can write this is as label 2 and these elements are label 3. So, except label 3 all the other labels are completely filled. Completely filled means they contain maximum number of nodes, and the last label So, it can be filled, or if it is not filled, then it should be filled from left to right in this direction. So, the last level here you can see it is filled from left to right, and the rightmost nodes are empty. So, we can say this is a complete binary tree. Suppose consider another example. So, here you can see, so this is a binary tree. Every node has at most 2 children. So, this is a binary tree, but here you can see for level 1 it has, or level 0 you can consider. So, in level 0 it has only one node. So, that is filled completely. Then L1 level 1, so here it has 2 nodes. So, it is also filled. Then it is level 2, it is also completely filled. Then the last level L3, so this one is not completely filled, but it is not filled from left to right. So, here for this node it is filled, then this node have no children. So, this node is have no children, and next this node has 2 children. So, as this node has no children and after that this node has children, so it is not a complete binary. So, it is not a complete binary tree. Why? Because it is not filled from left to right in this direction. So, this one is not a complete binary tree. So, we can consider another one example. So, this one, so this one, consider this one. So, this is a complete binary tree, because here you can see this is level 0. So, completely filled, level 1 completely filled, level 2 is not completely filled, but it is filled from left to right. So, if we delete this node, if we delete this node here, so now we can say this one is also a complete binary tree, because level 2 although it is not filled completely, but it is filled from left to right and the rightmost nodes are empty. Now, if I draw this figure is like this. So, now you can say this one is also a complete binary tree, because all the levels are full. So, in this way I hope you can understand the concept of complete binary tree. So, in complete binary tree all the levels are full except possibly the last level. That means, the last level may be full, may not be full, and if the last level is not full, so it is filled from left to right. So, the nodes we are going to put from left to right in the last level. So, the heap can be viewed as a complete binary tree. So, if the resulting binary tree is not complete, then we cannot say that as an heap. Okay. So, the first criteria for heap, it should be a complete binary tree, and another criteria for heap is like this. So, the keys in each node is greater than or equal to or equal to the keys in its children. So, the first one is, so this is the second condition. The first condition, it is a complete binary tree. So, these two properties should be satisfied. So, the first one, that means it is a complete binary tree, and second one, keys in each node is greater than or equal to the keys in its children. So, that means the key of parent or the value of parent should be greater than equal to the key of children. So, like this, or the value of parent should be greater than equal to the value of its children. So, we will take some example, then it will be more clear. So, now consider this one 10. So, its left child is 5, 7, 4, 2, then 1. So, now tell me whether it is a heap or not. So, for this we have to check these two conditions. So, is it a complete binary tree? So, yes, it is a complete binary tree. So, level 0 is filled, level 1 is filled, level 2 is not fully filled, but it is filled from left to right. So, it is a complete binary tree. So, the first condition is satisfied. Then what is the second condition? The keys in each node is greater than or equal to the keys in its children, or you can say the node that is at the parent should be greater than equal to its children. So, for the root node here you can see. So, 10 is greater than 5 and 7. So, it is okay. Now, come to this one, 5 is greater than 4 and 2, its children value. So, it is also okay. 7 is greater than its children 1. So, the second condition is also satisfied. So, now we can say as both the first condition and second condition is satisfied. So, we can say this one as a heap. So, this is a heap. Now, we will see another example. We will see another example. So, 10, 5, 7, 2, then 1. So, now first we will check whether it is a complete binary tree or not for heap. So, it is not a complete binary tree, because here you can say the last label is not filled from left to right. So, for 5 there is no left children or left child, but right child is there. So, this is not a complete binary tree. So, this is not a heap. So, now we will see another example. So, that is 10, or here we can see. So, 10, then 5, then 7, then 6, then 2, then 1. So, for this also we have to check whether this is a heap or not. So, the first condition, whether this binary tree is complete or not. So, yes, it is complete. So, first condition satisfied. Then second condition, whether the value of the node at parent is greater than its children. So, now we have to check for this node 10 greater than its left child 5 and right child 7. So, it is okay. For 5, 6 and 2. So, 5 is less than its left child 6. So, the second condition is not satisfied. So, we can say it is not a heap. So, this tree structure is not a heap. So, we will see one more example on this. 16, 14, then 10, 8, 7, 9, 3, 2, 4, 1. So, now we want to verify whether this is a heap or not. So, the first condition we have to check. So, whether it is a complete binary tree or not. So, here you can see. So, this is a complete binary tree because all the labels are full except the last label. So, last level is this one and the last level is filled from left to right. So, the first condition is satisfied. Now, we will move to the second condition, whether the value of the parent is greater than its children or not. So, 16 greater than 14 and 10, then 14 greater than 8 and 7, then 8 greater than 2 and 4, then 7 greater than its children 1, 10 is greater than 9 and 3. So, the second condition also satisfy. Then we can say this is a heap. So, this binary tree is also a heap. Now, we will move to the next concept. So, that is generally we have two types of binary heap. One is max heap, another one is mean heap. So, the heap that we have discussed till now is a max heap. That means, if the key value of a parent is greater than equal to the key value of its children, then we can say that is a max heap. And the reverse one, that means, if the key value of a parent is less than equal to its children, then we can say that heap is a mean heap. So, condition 1 is for both max heap and mean heap. That means, this should be a complete binary tree. So, whether it is max heap or mean heap, so the binary tree should be complete. And if the key value of parent is always greater than its children, then we can say that heap is a max heap. And if the key value of parent is always less than equal to its children, then we can say that is a mean heap. So, we have discussed several max heap examples. Now, we will take one example on mean heap. Suppose consider the mean heap is like this: 5, then 7, then 6, then for 7 the child is suppose 15, assume this is 17, for 6 assume it is 12, assume it is 11, now for 15 assume this is 25, so its child assume 27, for 17 assume its left child is 21. So, like this. So, here you can see, so this is a complete binary tree. So, all the levels are filled except the last level, and the last level is filled from left to right. So, here you can see this one, 5 is less than its child nodes 7 and 6. Similarly, for this one, 7 is less than its child 15 and 17. Then 15 is less than its child 25 and 27. Similarly, 17 it is less than its child 21. Similarly, for 6 it is less than 12 and 11. So, we can say this heap is a mean heap, and obviously this is a complete binary tree. Okay. So, now the max heap and mean heap part is clear. So, I hope you can understood this one. Now, we will see some properties of heap, or if we consider max heap. So, generally if we say heap, then it is max heap, and if it is written explicitly mean heap, then it is mean heap. Okay. Otherwise, in some questions they have explicitly written whether it is max heap or mean heap. Now, we will see one application of max heap and mean heap. So, where max heap is used and where mean heap is used. So, max heap generally used in heap sort algorithm. So, we will discuss what is heap sort. So, max heap is generally used in heap sort algorithm, and mean heap is generally used in priority queues. So these are the two applications of max heap and mean heap. So max heap is generally preferred in heap sort and mean heap is generally preferred in priority queues. And we have discussed about the role of priority queue. So priority queue is used generally in job scheduling, in communication networks and several other algorithms we have already discussed. So now we will see some properties of heap. So here you can observe the first one. The root of a heap, or I can explicitly write max heap. So root of a max heap always contains so this is C, always contains largest element. So in a heap or in particular max heap, so some authors have written heap in place of max heap, so do not confuse in that. So root of a max heap always contains the largest element. So in the example that we have already discussed, so always the root is the largest. So we will take one more example on this. Suppose a max heap is like this. So assume then 8, then 6, then 4, then 5, then 1, then 2. So here, so the first condition is satisfied, it is a complete binary tree, and the second one, here you can check the key value of parent is always greater than its children. So here for 10 it is greater than 8 and 6, for 8 it is greater than 4 and 5, similarly for 6 it is greater than 1 and 2. So we can say it is a max heap. So in the max heap you can find the root node has the largest element. So here the largest element is 10. So we can find the largest element is 10 here, that sits at the root. So this is one important property. So root of a max heap always contains largest element. Similarly for a mean heap, the root of a mean heap always contains the smallest element. Now another important property we can see here. So the path from root to leaf, from root to leaf in a max heap, is decreasing, or we can say non-increasing when the same value is allowed. So here you can see for the condition for leaf is parent is greater than equal to its children. So when the same value is allowed as parent and children, so there the path is non-increasing. Otherwise it is, if distinct values are there, it is decreasing. So non-increasing. So we will see one example. So here you can see the path from root to leaf in a max heap is decreasing or non-increasing. So we will see one example. So here you can see. So this is a max heap. So now we will see the path from root to leaf. So we can consider this path. So 10, 8, then 4. So it is decreasing. Similarly, you can consider this path from root to leaf. So, you can also find here non decreasing. So, 10, then 6, then 1. So, you can find it non increasing, sorry. So, 10, 6, 1. So, it is non increasing or decreasing. So, we can also allow same value in a heap according to the example. So, let me copy this one. So, copy, paste. Okay. So, here I can write 10 in place of 6. So, I can write here 10. It is also a max heap, because here you can see the value of parent is greater than equal to its children. So, here 10 is greater than equal to 8 and 10. So, here 10, 10 same values are there. Then it is also a heap, no issues, because we have written here the parent value greater than equal to children. So, greater than equal to condition is there. So, you can check. So, 10, 10. So, same value is there, no issue. So, equal is there. So, it is also a max heap. So, if we consider this path 10, 10, 2. So, it is non increasing path, non increasing path. So, when same values are there or repeated values are there, so the path is non increasing. When distinct values are there, so in a heap, if all the values are unique or distinct, then we can say the path is decreasing in a max heap, the path from root to leaf. Okay, so I hope this one is clear. Now, another property is that here you can see, so no relation in same level. So, in a heap there is no relation between the nodes or key values in same level, or we can say no relation between left and right subtree of a node, or no relation between left and right child of a node. So, only heap says about the relation between parent and child. So, it has no relation between the nodes that are in the same level. So, here 8 and 10 are at the same level. So, there is no relation between them. We cannot say always 8 is greater than 10, or always the left child is greater than right child, or the right child is greater than left child. We cannot say it like that. Similarly, here you can say, so this is another level. So, level, if I say this is level 0, this is level 1, this is level 2. So, there is no relation between the nodes that are in level 2. We cannot say the relation between them, which one is larger, which one is smaller, we cannot say. So, it is not defined. So, here you can see this point, no relation in same level or left and right subtree of a node. So, here consider this one. So, here 10 is the parent. So, left child is 1, right child is 2. So, we cannot say whether left child is greater than right child or right child is greater than left child. So, like that. We cannot say the relation between left child and right child, but only the relation between parent and children we have to consider. So, I hope this part is also clear. No relation in a same level left and right subtree of a node. Path from root to leaf in a max heap is decreasing when distinct keys are there, and non increasing if some key value is repeated. And root of a max heap always contains the largest element. So, in a max heap we can find the largest element. Similarly, this path from root to leaf in a max heap is decreasing. For a mean heap it is increasing or non decreasing. Okay, so I hope these properties are clear. So, these are simple properties. So, based on the concepts that we have discussed, we will solve one previous year question. So, a simple question you can find how easy questions are asked in the exam. So, here you can see. So, we have discussed the concept Now we will see the simple question. A max heap is a heap where the value of each parent is greater than or equal to the value of its children. Which of the following is a max heap? So here options are not written, so I am writing the exact options that are asked in the exam. So 10, then 8, then 6, then 4, then it is 5, so it is 1, then 2. So this is one option A. Then in option B, so it is 10, 8, 6, then 4, 5, then 1, 2. We have another option C. So 10, 5, then 6, then 4, then 8, then 2, then 1, then D. So 5, 2, 8, 1, 4, 6, 10. So among these options, so these are the exact options that were asked in an exam, and the exam name I am explicitly writing. So it was asked in GATE 2011. Okay. So you can imagine how simple questions are asking in GATE exam. So here you can see a max heap is a heap where the value of each parent is greater than or equal to the value of its children. So this is the definition of max heap. So property 2, and property 1, it should be a complete binary tree. So which of the following is a max heap? So which of the following trees that is given here are complete binary tree and satisfy the properties of second property of max heap? So first property for option number 1. So whether it is a complete binary tree, so here you can see 10, then 8, 6. So this label is complete, this label is complete, but label, if we consider this is label 0, this is label 1, this is label 2. So label 2 is not complete. Here you can see for 8 there is no right child, and although it is not complete, then it is not filled from left to right. So once this is complete, then we can move to the next level. So this one is not complete binary tree. So this is not a heap. So according to the definition of complete binary tree, all the labels are filled except the last label. So here the last label is this one, and all the labels are filled. So this label is not filled, and the last label should be filled. If the last label is not completely filled, it is filled from left to right. So this is the definition of complete binary tree, and this option A does not satisfy the first property of heap, that is not a complete binary tree. So now come to the second option, option B. So whether it is a complete binary tree, so yes, here you can see, so this label 0 is filled, label 1 is completely filled, label 2 is completely filled. So it is a complete binary tree. So now we will move to the second property. So we will check whether the value of parent is greater than its children or no. So 10 greater than 8 and 6. So for 10 it satisfies. For 8 it is greater than 4 and 5, it satisfies. For 6 it is greater than 1 and 2. So both the two properties are satisfied for option B. So you can say option B is the correct heap. Now we will check for option C. So here option C, for root value it is 10. Then so first we will check whether it is a complete binary tree or not. So here you can see all the labels are completely filled. So you can say option 1 is satisfied. Now for option 2, so we will check the value of parent is greater than the value of its children or not. So 10 greater than 5 and 6. So for 10 it is satisfied. Then 5 should be greater than its child. So 4 and 8. So here you can see 5 is not greater than 8. So here the property is violated. So we can say this one is also not a heap. Okay. So now we can see the next one. So whether it is a complete binary tree. So, yes, it is a complete binary tree, all the labels are filled. Now, we will see the second property, that is whether the value of its parent greater than its children or not. So, 5 should be greater than its children. So, 5, 2 and 8. So, here you can see 5 is less than 8, that means the value of the parent is less than the value of its children. So, this property is violated. So, we can say this is not a heap. So, only option B is correct, and this question was asked in GATE 2011. So, which of the following binary tree is a heap? So, it is a simple question. You can imagine how simple question. Okay, so we will continue the representation of heap in the next video.